So this is my redo of standard 2.2, the charged particle in a magnetic field. I have a positive particle with charge q with this initial velocity and this initial position, and the magnetic field is in the positive x direction coming out of the page. So the first thing that I did was to find the force and set it equal to mass times acceleration. So in this case, F equals q times velocity across the magnetic field, which gives me this expression, and it can be broken down into its components. So I get mvx dot equals 0, mvy dot equals negative qbvz, and mvz dot equals negative qbvy. And I just labeled these equations to refer back to them. So I first took equation 2 and differentiated it with respect to time and solved for vz dot so that I could plug this expression into equation 3. And so I did that and got a differential equation for vy. So I got vy double dot is equal to negative omega squared vy, and I just defined omega as qb over m. So the solution to this equation we know is a linear combination of sines and cosines. So c1 sine omega t plus c2 cosine omega t is equal to vy. And using the initial condition, we know vy of 0 equals v naught y. And when t equals 0, you're just left with c2. So that's what c2 is. Just rewriting vy. And then we know from equation 2 that vy dot has this relationship with vz. So I took the derivative of vy, which is right here, and I put it into equation 2. And simplifying it, you get that negative vz equals c1 cosine omega t minus v naught y sine omega t. And going back up here, so we get this expression for vz of t, and then we can use the initial condition for vz of 0 is negative v naught z equals negative c1. So that solves the c1 constant for both vy and vz. So rewriting them, we get these expressions for these velocities. And then for the velocity in the x direction, because v dot equals 0, it means that vx is constant. So we'll call that c3, and vx of 0 is just c3 and is equal to v naught x. So we have an expression for the velocity and all the components of the velocity. So then to find the equations of motion for each direction, you integrate the velocity with respect to time. So for x of t, you just get v naught xt plus another constant c4. And we know that the initial position for x is 0. So c4 is 0. So x of t is just v naught x times t. And then you do the same thing for y of t. You differentiate it and you get another constant, which is I'm calling c5. And we know that this whole expression evaluated at t equals 0 is equal to y naught. So you get c5 equals y naught plus v naught z over omega. And so now we have an expression for y of t. And the same process for z of t, integrated the velocity in the z direction and get an expression for that constant. And then all in all, you can get this whole equation for each component of the position vector. And then I plotted that in Mathematica. And so right now I just have all of my variables set to 0, and if I increase the v naught in the y direction, if the computer wants to work, it should show me a circle. which it does. And then that's, let's see, oops, so that circle is in the ZY plane. ZY. And then if I increase the V naught in the X direction, that will give me a helix type of motion. Which you see, the typical motion for a particle in a charged field.